Alright, hello and welcome to a new video in a graduate series on probability theory. We've previously defined random variables and probability spaces, and we've said that for every random variable there's an associated function, which is its density, its distribution function, excuse me, and it's defined as the probability of x less than or equal to x. And then we also associated the other function, which is the density function corresponding to the random variable x. Now, a natural question to ask is like, why are we giving this function a name? Like, sure, one might be interested in finding this probability, but why are we giving this specific function a name and like giving it this letter f, and why are we giving it, like, why is it important in the first place? So just to motivate a little bit the importance of this function, what I'm gonna do is I'm gonna show you an application of this distribution function. So consider the following simple problem. Suppose we have a normally distributed random variable with mean 0 and standard deviation 1. And by that I mean the random variable has the density function that is given over here. It's 1 over square root of 2 pi e to the minus x squared over 2. So we ask a natural question now, or a simple question. What's the density function for x squared? I mean, x squared is a random variable, and usually in probability theory, we're not only interested in random variables, but rather we're interested also in functions of random variables. And if we consider the squared of a random variable, the square of a random variable, it's natural to ask, what's the density function for this? What's the distribution for this? And so on and so on. So answering such a question would require us to use or can be done by using the distribution function. So let's go ahead and do this actually. So recall the the distribution function for the random variable y is just the probability of y less than or equal to y by definition. But then y is x squared, and hence we get that this is the probability of x squared less than or equal to y. But then we can continue simplifying this and rewrite this as the probability of x less than or equal to square root of y bigger than or equal to minus square root of y, because we have information about x, and hence it's good to go back to x. But then since we have information about x, this means we know how to evaluate this probability, namely by integrating the density function. So we can integrate from square root of y to minus square root of y to square root of y. We can integrate the density function of x. All right, and now we need to make a good observation, which is that this function is an even function, right? Since it's an even function, this thing is literally just 2 times the integral from 0 to square root of y f sub x of x dx. And now what we can do is the following. What we can do is we can rewrite this as 2 times the integral from minus infinity up to square root of y of f of x dx, and then we need to take away the additional integral that we've put here. Namely, we need to take away the integral from minus infinity to 0 of f of x dx. And notice how nice this is, because this thing is literally by definition f sub x of square root of y, because this is how we defined the distribution function. And this thing is by definition f sub x of 0. It's just a constant. So that is to say, we now have that this is equal to 2 times this minus that. So now, given that we know the density function for x, we can get the density function for y as follows. So by definition, the density function for a random variable, it's the derivative of its distribution function. So in this case, what we can do is we can take derivatives, and we'll see that this will leave us with the following. So f sub y prime, so maybe we should start by little f sub y. So little f sub y, which is the density of f at y, is basically just the derivative of big F sub y at y, and that's just the derivative of this function, because the other part is just a constant, times the derivative of the square root of y, which is 1 over 2 square root of y, I guess. And then you observe that this will leave us with 1 over square root of y times the density function evaluated at square root of y. But we know what the density function is, so we can just plug in, and we see that this is 1 over square root of 2 pi y times the exponential of minus y squared over 2. If we plug in square root of y in f, this is what we get. But we need to be a little bit more careful here, because observe here that we just literally took square root of y. So this is all valid for y bigger than or equal to 0. So this is all valid as long as, actually let us just do it this way. So this is all valid for y strictly bigger than 0. And then we see that this thing that we've written here is valid for the square root of y for y strictly bigger than 0, and hence the formula for f sub y for all y can be written as 1 over square root of 2 pi y times the exponential of minus y squared over 2. This is for y positive, and it's 0 otherwise. What's interesting over here is that, as usual, like we have this nice property of the density function, which is that it integrates to 1. So if we integrate this density function, we get 1. So this is by definition. So up till here we solved the question that I asked. So this would be excuse me, this is y, not x. This would be the density function for y. However, and of course, like from this, we can get the distribution function, or the probability of any like pre-image of y, if you wish. Any pre-image, we can get like the pre-image of any set under y. Before we wrap up this, actually, I just want to show you a little quick application of this, because this is very nice. So remember that we have this nice property of density function, like they actually integrate to 1. And from there, we can basically get a property of the gamma function. So let me just show you this application. So as another application of let me just call it of 3, is that if you recall that the gamma function, it's basically this function defined for real of z. I mean, it can be analytically continued, but for us here, we just for this application, we only care about it for real of z bigger than 0. So this is the function defined as t to the z minus 1 e to the minus t dt. We're integrating with respect to t from 0 to infinity, and this is defined for real of z positive. I wanna verify using 3 that gamma gamma at 1 over 2 is square root of pi. Let's see how to verify this. This is a nice application. So if you like, basically if you just Google this, you see this is a very famous property of it. Okay, so let us actually verify that gamma of half is square root of pi, and the way we can do this is by just noting that this thing is a density function, and hence the integral of it, which is the integral from minus infinity to infinity of f sub y at y dy, is 1 because it's a density function. But remember that, I mean, for y less than or equal to 0, there's nothing, it's just 0, so we can restrict ourselves to this interval. Yeah, and excuse me, I've probably done a typo here. It's a y, it's not y squared, because we've inputted a square root of y, so there's a y here. So going back to the example, if we integrate that distribution, that density function, this is what we have, and hence from here we see that this is gonna be just like if we do the change of variable, we send, I don't know, we let x be y over 2 and change this integral, we see that it's gonna be gamma at 1 over 2. Or maybe I should write it this way. It's gonna be 1 over square root of pi times gamma at 1 over 2. So after you do this change of variable, this is what we have, and we can just get that gamma at 1 over 2 will be square root of pi. And this is a very interesting thing to observe.